Today we're going to go back and look at some more motion. In fact, we're going to look at some things that go around in a circle. The first part of today's activity is going to involve a paper plate and a marble. Let's take a look at the motion we want to look at. The first motion I want to investigate is this marble moving around this plate. We're going to be looking at the speed of the marble, the velocity of the marble, but most importantly, the acceleration of the marble. Let's stop this marble right here and talk about what the velocity, acceleration, and direction this thing's moving at this point. Okay, I think we can all agree that the marble at that point around this circle, when the marble is right here, the velocity of the marble is actually in this direction. It's moving that way. We can see that if we actually have a cut in the plate. All right, let's take a look at what happens when I actually take part of this edge off the plate. So I'm going to take my marble and roll it around the plate. What happens when it gets to this spot? What direction does it go? If I do it the other way, actually I have two plates here. Let's do this, just this one. It continues in a straight line here, or it continues in a straight line here, tangent to the circle. So what you can see here is you're actually looking at inertia. If the plate is gone at this point, like you saw, the marble continues on a straight line out there. The inertia of the marble at this instant is in this direction. It's tangent to the circle. Okay? So let's take a look at the marble at another spot. Let's take a look at it up here. If we look at it up here, the velocity of the marble is also tangent to the circle. So, in this, if it goes from here, this angle here, to this angle here, it actually does change the velocity. Now I'm going to be very clear on that. The speed does not change, but the velocity does change because we had a change in direction. Remember, velocity is not just speed, it's speed and direction. So let's see how that works. If this is our initial velocity, this is our final velocity. So if I draw these two as vectors, kind of do it head to tail, if you remember how we did head to tail, we had velocity initial, we had velocity final, which is right here, is going this direction. So the change in velocity is right here. So we draw them head to tail. The velocity here, the change in velocity to the resultant, which is the final velocity here. Now that's if we look at the marble in these two spots. What I'm most interested here is the direction of this change in velocity. So let's take this, and this is actually over about a quarter of a revolution. So let's take it a little bit smaller so we can get more down to an instantaneous velocity. So if we look at an instantaneous velocity, so we've got a velocity that's going this direction, and then let's go like here, and it would be going this direction. So this is V naught, this is V final, right there. So we're going a little bit smaller time. We're not looking at a quarter of a revolution, we're actually going to get smaller and smaller. If I could, I would go to infinitely small, but I'm not going to do that. So if I do this, I have velocity initial here, velocity final here, the change in velocity is there. Velocity 1 plus the change gets you velocity final. It's actually going to be looking, what direction is this? What direction, if I draw that again, this is my change in velocity. What direction is that? Well, it's actually pointed towards the center of the circle. So we have this change in velocity pointed towards the center of the circle the whole time around. If we look at an instantaneous change in velocity, like a very quick change in velocity, it's moving towards the center of the circle. Now this does happen over a small amount of time, microsecond, millisecond, whatever. So we'd actually have a change in velocity over time, which we know as acceleration. Now, what we know about this acceleration is we know that it has to do not with a change in speed, but a change in direction. This is actually called centripetal acceleration. Sometimes they call it radial acceleration. The centripetal acceleration is the acceleration that keeps something in a circle. And it actually points towards the direction of the circle, or the center of the circle. Our equation for centripetal acceleration is v squared divided by r. Now there's a derivation for that, I'm not going to get into it, but v squared, the velocity that's around, the instantaneous velocity that's moving around, divided by the radius. Okay? Now, it's important to note that the velocity is tangent to the circle, the acceleration is towards the center of the circle. Now, this marble or stopper or whatever it is that we're going around the circle also has a mass. And you can imagine that the more mass it has, the more inertia it has, the harder it is to keep in a circle. Which means not only do we have a centripetal acceleration, an acceleration towards the center, we also have a centripetal force. The centripetal force is equal to mass times the centripetal acceleration. It's the same equation that we've always had from Newton's second law, which another way to write this would be mv squared over r. So this centripetal force is the key to solving these problems. Centripetal force is what keeps things in a circle. So if you look in my plate, when we're looking at the plate with the marble, the edge of the plate is actually pushing the marble towards the circle. If that plate edge isn't there, like when I cut it out, the marble continues on. The edge of the plate is supplying the centripetal force. If we look at a stopper on a string, as this thing spins around, what is supplying the centripetal force? What is keeping it in a circle? Well, in this case, it's the tension on the string. If I cut the string instantly, maybe when the stopper's up here, it'll continue to go in a straight line. Whenever we solve any of these centripetal force problems, the question always is, what supplies the centripetal force? What force is keeping it in a circle? Let's look at an example of this idea of centripetal force with inertia. So here I've got a glass of our beaker full of water. And the water, in this case, gravity is pulling it down, keeping it in the bottom of the container. Now, what I can do is, this thing has inertia. If I start to move it like this, the water is going to continue to move this direction until it hits the side of the container, it kind of bubbles up, then it comes back the other way. But if I take this beaker and take it all the way around my head, I can make it so the water doesn't fall out. Now let's think about this for a second. When the beaker is at the top, as long as I have a fast enough speed, it has inertia that the water wants to go in this direction, not down. So as it tries to go that direction, I push it down. The bottom of the container pushes the water down and keeps it in a circle, which is why it stays in the bottom of the container. This is actually an object's inertia. There's another force called centrifugal force, not centripetal, which is what we're talking about, centrifugal force. And it's actually not a real force. There's no such thing truly as centrifugal force. The idea of centrifugal force is the normal force of this thing, or the water pushing into the bottom of the container. The water is pushing down into the bottom of the container. But technically, that's not a force. That's just the object's inertia. It's a result of an object's inertia. Another example of centrifugal force is if, let's say, you're in a car and you go around a corner, or maybe you're in a roller coaster and it hits a corner really quick. You get thrown into the door. So you feel yourself being pushed into the door. You feel yourself being pushed. You're actually not being pushed. Your inertia is trying to keep you going in the same direction. The door actually pushes on you with centripetal force. You feeling yourself being pushed isn't actually happening. It's you trying to stay in a straight line. That's called centrifugal force, which isn't actually a real force. Centripetal force is. Thank you so much for watching. If you like science and you like this video, feel free to like this video below. and subscribe for future updates.